Okay, in this problem, we are determining the resolution of the Hubble Space Telescope in visible light. The primary mirror has a diameter of 2.4 meters. So if we draw this example here, we're going to have our mirror. This is our detector. And we're going to imagine that we have objects way out here. And we're trying to determine what our size of our airy disk. So our size of our airy disk, this is the size of our airy disk here. And and looking here, we have the visible light is an important thing. So that tells us that lambda is equal to, let's say, 550 nanometers. That's like in the green. Our diameter is d, and so that's equal to 2.4 meters. And we're trying to find our theta, so this theta here, that theta. So we're going to use our airy disk formula or our diffraction formula for a circular aperture. So we're going to have theta 1 is equal to 1.22 lambda over d. And theta 1 is the angular extent of this, this angular extent here. And this, remember, comes from the Bessel function. So there are Bessel functions, and it takes one of the terms of the Bessel function. We can figure out what this is. We can say 1.22 times 550 nanometers. And actually, we'll say that we're going to do meters instead. So we're just going to cross this out. And so to the minus 9 meters divided by 2.4 meters. And when we do that, we get theta 1 is equal to, let's see, 2.8 times 10 to the minus 7 radians. So our measure is radians. And so if I want to find this, this is a pretty small resolution. And that means I can distinguish stars that are pretty close together, in astronomy terms. And so what I can do is I can multiply this by 57.3 degrees per radian. And then I can multiply that by, so I'm going to get degrees out. My radians are going to cancel. And then I can say I have 3,600 seconds per degree, right? And when I plug that into my calculator, I get 0.05 arc seconds. And so if I were to write that, for somebody in astronomy would say my resolution is equal to 50 milliarc seconds.